Hello everyone. Today we are going to do a 2D simulation of a SAW device using COMSOL and find its resonant frequency. For that, I have taken a random paper. I'll put this paper in the description if anybody wants to see it. Have a look at it, and I'll put a link of this paper. So in this paper, they have found the resonant frequency of a SAW device experimentally. So we can use this as an example for our simulation. So they have taken the thickness of zinc oxide layer to be a 1.5 micrometer. The thickness of silicon substrate was not given, or maybe I couldn't find it in this. So I have taken a random value of 400 micrometer, uh, and they have taken the thickness of aluminum electrode to be 150 nanometer, and the wavelength is 32 micrometer. So from the wavelength, uh, we can understand the pitch. So for a SAW device, the lambda is equal to 2 into pitch, where pitch is the distance between the center of adjacent electrodes. So here, so if you have two electrodes like this, then the pitch is this distance between these two electrodes. So V is equal to nu lambda, where V is the velocity of the wave, V nu is the frequency, and lambda is wavelength. We know this equation, right? So for the velocity of Rayleigh wave that is moving through the surface of zinc oxide. So a Rayleigh wave, there are different type of waves in surface acoustic waves like Rayleigh waves, shear horizontal waves, etc. So you can have a look on what those waves are. And if you want to me to do a video on that, I can do that. Please put in the comments. And so for a velocity of this much and a wavelength of 32 nanometer, we can find a frequency using the formula above. And let us see by simulation whether we are getting this resonant frequency using COMSOL. So now we can see in simulate this audio device in COMSOL. In COMSOL, we start by clicking the model wizard. So since we are going to do a 2D simulation of this audio device, we can click 2D. In this, we select structural mechanics and click done. So whatever studies we want to do, we can add as and when we need it in COMSOL. So first initially we are taking structural mechanics. Yeah, so it has opened. Now here initially our geometry is in micrometer. So we set the geometry to be in length unit in micrometer. Then in geometry we choose rectangle. So first we have to make the substrate structure, like here substrate is silicon. So I take the width of 32. So why I take width 32? Because that is our wavelength lambda. So we are taking only a small part of this OR device and simulating. This will have only two electrodes. Actually, a SAW device will have many electrodes on top. So for simplicity, we are taking only two electrodes, and we are taking 32 because that is our lambda. And the height we have discussed it to be like 400 micron I'm taking. And this is on the origin, like xy. So, this is the position where you have to define where you want to keep the structure. And then I want to on top of that I am need to put my next structure, which is the zinc oxide. So for that I'm defining another rectangle, and that also the width is same, 32 micrometer, and height is 1.5 micrometer. So I want this on top of the silicon substrate, right? So the silicon substrate height was 400. So I need on top of that. So that is what I need. And x is 0. Is it? So I want x. So I think you must have understood that this is the coordinates where so which helps us to put these blocks at places where we exactly want them to be put. And then when we so that's not it, right? We want to put two more electrodes on top. So for that I choose another rectangle. And that electrode, where should the electrode be? So one electrode should be in such a way that I should make a design in such a way that the distance between these two electrodes is 16 micrometer. Distance between the cell of electrode. So I am making an electrode. So so the electrode size should be. I'm taking a 8 micron. The second electrode also I'm taking a 8 micron, and the distance between them is also 8 micron. So so the width of the uh, electrode is 8. The height we have discussed it is 0.15, 159 millimeters. So it's 0.15 micron. And where should this be? This should be at an x value of 4 and y of 400. Because this will no, no, 400, it will be 400 and 1.5. It should be above both the uh, substrate and the zinc oxide surface, zinc oxide material deposited, right? So it is 400 and 1.5. So then I need to also define the second electrode, which also has the same width of 8, height of 0.15. Then where is x? So we have now kept it 4 plus the next electrode, which is 4 plus 8, which is 12. And the distance between electrodes we have taken as 8. So 8 plus 8, 16 plus 4, 20. So it's 20. So and y should be at how much? 401.5. So you see, we have 4 at the two 4 micron the two edges, 2 electrode 8 each. So 8 plus 8, 2 electrode 16. Distance between them is 8. So 8 plus 8 plus 8, 24 plus 2, 4 micron the size. We shall all make it to 32 micron, that is our lambda. And now we're done with the structure. So fill our objects. So we need to minimize this to see it. So we're not able to see it. Okay, here we can zoom in to see our electrodes on top. See, this is our electrode. Okay, so now we need to start putting the boundary conditions needed for this SAW device. So what is one boundary condition? One boundary condition is that the bottom should be fixed, right? So for these boundary conditions, I need to uh, add a study. So for that, you have to choose solid mechanics. So choose solid mechanics. Okay, and in solid mechanics, I need to choose a fixed constraint. So and I need to fix my bottom, right. So I'm zooming out and here. So I fix my bottom using the constraint. And the edges I need to fix using a constraint called the uh, periodic condition. So so this structure is not just one, right? So I need to this structure actually extends as much as there is, right? So we have only taken one lambda, so the structure is even bigger actual structure and only two electrons. So for that we need to put it like a periodic condition on the edges of this structure. So for that I will choose the boundaries. In boundaries I will select periodic condition. So where all I have to give, the four sides I have to give as periodic condition. So for that I need to select the four sides. So this is one side, then this side, then this side, and finally this side. So now I have given the boundary condition. One is a periodic condition and one is a fixed constraint. So now after this, what else should I give? So the next thing I should be focusing on is the, so zinc oxide is a piezoelectric material, right? So in order to excite a piezoelectric material, I should give it some voltage, right? So our next thing is to do that. So to put a ground and also the voltage. So for that I am choosing electrostatics. Electrostatics I need to put the ground. So I am zooming in. So one electrode I am putting as ground. So here zoom in the electrodes. So this edge, top edge, both the sides I have, so all the 4 points I have put in as ground. Now next I should do is give it a potential, right? That I am going to give in the next chapter. So I choose the terminal. In terminal I choose voltage. So it's already set 1 volt. Yeah, you can do with 1 voltage. So here then I select the four sides for applying a potential. Yeah. So once that is done, so now we have given the ground and the voltage, right, to excite. So now we should think what next to for our device, for us to simulate our sound device. So we need to find the frequency, right? So 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 till now we haven't given what is the material. So this is of zinc oxide. The top of that we need to put CS, put two electrodes, right, which are actually we are going to put deposit aluminum. So so now we can choose the material. So here you choose the material, add material library. Then the material we can first choose a substrate. So in MEMS you just stick semiconductors. There you can select silicon. Yeah. So silicon selected. Next material I want to select is zinc oxide. So add materials library. Then piezoelectric. Yeah, let me search for zinc oxide. So you can see a lot of different piezoelectric materials are here, like aluminum nitride, barium titanate, etc. So here we will choose zinc oxide. And we also need the material for electrodes, that is aluminum. So I'm going to choose aluminum for electrodes. From metals, aluminum. So I'm going to add that also there. Yeah. Now I need to select which, so zinc oxide is 2, right? So I select this. So this is the second, so I have selected, it has come here. Now I need to select the two electrodes, that is aluminum. So for that I need to zoom in again. So this is one, this two. That is done. So So now 1 is silicon, 2 is zinc oxide, 3 and 4 are aluminum. Now here in solid mechanics we need to add a few more things like since we are using a piezoelectric material, we need to select that material model as piezoelectric material. And since this is taking some time for it to come, yeah. So now you need to select that. So zinc oxide 2 is what is the piezoelectric material like. Also, we need to give details about the other materials also, right? Whether they are isotropic, anisotropic, etc. So I'm going to duplicate this thing here. So here I'm going to give silicon. So number one is silicon, right? So all the others I can delete from the linear elastic material to delete. Just press delete. Click and press delete in your keyboard. Now in this I need to make my silicon is anisotropic. So I choose anisotropic. Then when I see now 3 and 4 are aluminum, which also I should be setting to anisotropic. So now all that is done. Then then now we need so also we need to select periodic condition for electrostatics also, like what we did for solid mechanics. So here we will select periodic condition and then give the four sides: 1, 2, 3, and 4. Yeah, that is done. Now after that, before we had so here yeah, here you can see two crosses here. So this gives us that some material property is missing in this, so we need to check that whether that is there. Yeah, so relative permittivity of silicon is not given, that we will give it as 11.68. This you can just find in Google, that is 11.68. Then for uh, for aluminum you can see that this here also they are asking relative permittivity, but for metals you know that the relative permittivity is infinity. So then we understand there is some problem there. So the problem is here. So the uh, electrodes 3 and 4, the charge conservation is not applicable there. So in that case, we delete 3 and 4. So this will avoid those problems we had there. Also, we also need to put a charge conservation for uh, the piezoelectric material. So yes, so we add that, and then we know this is the number two is the piezoelectric material. So we add that also, and then we see yeah, you can see now. Now that is gone. So what happened? We have removed the electrode 3 and 4, so such that the charge conservation there doesn't is not applicable, to make it non applicable. So so why charge conservation not applicable? Because these things are actually solved based on this equation, like relative permittivity, epsilon zero epsilon r, things like that. So we don't want, so we don't know the relative permittivity. We know that the relative permittivity of a metal is actually infinity, right? So in that case, we need to make the charge conservation not applicable uh, for the simulation to work fine. Now we can see the terminal. Only the bottom terminal is now there. Initially we had given all the four sides, right? So now since we have removed 3 and 4 from aerostatics, that charge conservation not applicable in the electrode, and made the charge conservation not applicable there, we have actually fixed the problem. Now in multiphysics, we have to give piezo trig effect. Then I think we have almost given all the boundary conditions and all the all the things that is needed for simulation. Uh, then now we need to build a mesh. So now I'm just giving the auto mesh that is already there. I'm just building it. So I am making the element size final, and now we need to look at the study. So what is the study we are looking at? We want to find the resonance frequency, right? So for that we need to choose the eigen frequency study. So choose that there. So remember, right? So we had actually initially found out what was the uh, resonance frequency. It was 136 megahertz. So we need to search around that area. See, it like search around frequency. So I'm giving it around 130 136 megahertz. Okay. So this is the desired number of frequency. How many number of uh, do I want to test it for? So I will give around 30 different frequencies around 139. It will stimulate and show us the different modes around all those different frequencies. So we are looking for the Rayleigh waves because we have taken the velocity of Rayleigh wave. And now let us compute and see. Before that, we'll just check whether we have given everything fine. We have given all the geometry, all the four geometries. We have given the material. And there doesn't seem to be any error over here. Mm, Now we can uh, run the simulation. Compute. This will take some time. Yeah, we have got it. We can see the different. We are expecting around 139. Let's see what we are getting. Um, so we'll just increase it. Since it is surface acoustic waves, I'm mainly looking at the surface. So I'll take this much region. Yeah, that will be better. Yeah. Now so we have given 30 different points, right? So we have got like they have just been done for this much many frequencies. So we will check at what frequency we are expecting around 136. Let's see where we have got it. 127, 130, 135. Yeah, we have got it around 139. We have got it at 139 actually. 139.16. So this is the Rayleigh mode. So here you can see that. So to make it a bit more colorful, like a rainbow color, I can change the color. So here from here I've selected surface in mode shape, and then I'm going to change the color to rainbow color. So yeah, so see, this is the Rayleigh mode. So we have got the Rayleigh mode around 130 9. So I've set, so this, so since actually the wave is so our thickness of zinc oxide here is actually 1.5 micrometer, right? But the wave can actually go for 1 lambda. It can go even, so what is our lambda? Lambda is 32 micrometer. So our wave can go even deeper, right? So the wave is not just on zinc oxide, it is also going to silicon substrate. So thickness of the silicon substrate and the properties of silicon also matters. So so that is why we didn't get exact 136, we got 139 in the simulation. So this is the Rayleigh wave. There are also shear horizontal waves also, which you have to stimulate for particular velocities of the zinc oxide. That you will have to do some uh, um, pair, do some research and find out what is the velocity, and and based on that you can find what is the you can fix your lambda, right? And then based on that you can find what is the eigenfrequency and stimulate for that um, shear horizontal wave also. So this is the Rayleigh wave which we have simulated. So finally, this is how we can do a 2D simulation of solid waves and find its resonant frequency. Thank you.